see the recording video? So the recording video after the session is over, I'm generally sharing in your WhatsApp group. So you can have a look in that recorded video link. Along with, I generally share the study material and lecture materials in the group, so you can have a look on that one also. Okay. So just to confirm from my side whether my screen is visible to everyone.
Yes, sir.
Okay, thank you. So as we can go as per the contents of our VLSI system design as per the syllabus which we have. So in the morning we have started with the combinational CMOS circuit. So it is just a continuation of that combinational CMOS circuit. So so next unit is basically dealt on ratioed circuits. Okay, we can see in the figure. So this is actually in the figure is NMOS ratioed circuit. The ratioed circuits actually depend mostly on the proper size or resistance of the device for correct operation. So if you need a correct operation of the devices, so it is very required that a proper size or resistance of the devices is very important. For example, in the year early 1980s or 1970, that means when the CMOS technology was not came into existence, so the circuits were preliminary built with the NMOS transistors only. Okay, so that we can see here in this figure. So we have a NMOS transistor here. So conceptually, the ratioed gate that we generally call, so that ratioed gate consists of a NMOS pull down network. Okay, so as you know, our PMOS network is generally considered to be pull up network, and our NMOS transistor is considered to be pull down network. So conceptually, if you can say, this ratioed gate consists of an NMOS pull down network and some pull up devices called static load. Okay, the static load, if you can see here. So when the pull down network is off, the static load pulls to output 1. Now when the pull down network turns on, it fights the static load. Now, the static load must be weak enough that the output pulls down to the acceptable 0 here. Hence, there is a ratio constant between the static load and pull down network. Now, the static load which we have, that stronger static load produce faster rising outputs, but increase in output low voltage, that is our VOL, degrade the noise margins. Okay, so noise margins, if you remember, we have studied about noise margins when we discussed about the propagation of the digital signals in the inverter circuits, if you can remember. So in that cases, we discussed about the noise margin. So the static load generally produce faster rising outputs, but it increases the output low voltage, and that eventually degrade the noise margin and burn more static power when the output should be 0. And unlike complementary circuit, the ratio must be chosen to the circuit operates correctly despite any variation from the nominal component value that may occur. Okay, so this is actually I have taken from the reference from the book CMOS VLSI Design by Neil H. E. West, the book. So if you can see here, this is actually the CMOS, what you can say, this P pseudo NMOS inverter and DC transfer characteristics. Okay, so this is the, you know, right, this is the output characteristics for the transistor, and this is our this is the output characteristics, and this is our transfer characteristics. Okay, so this is actually the pseudo NMOS inverter and DC transfer characteristics. Now there is another concept that we call it cascode voltage switch logic. So what is that cascode voltage switch logic that we commonly abbreviate it as CVSL? Okay. Now the CVSL seeks the benefit of the ratio circuit without the static power consumption. Now it uses both the true and complementary input signals and compute both true and complementary outputs using pair of NMOS pull down network that we can see in the 9.20. Okay, in this figure, if you can see here. So the pull down network F, this the pull down network F uses inverted inputs feeding transistor arranged in the conduction complement. Okay, now for any given input pattern, one of the pull down networks will be the on and other will be off. Okay. Now the pull down network that we generally consider that is on and will pull that output low. Now this low output turns on the PMOS transistor to pull the you can say the opposite output high. When the opposite output rises, the other PMOS transistor turns off, so no static power dissipation occurs. So if you can see in this figure B, okay, this is the figure B. So the cascode voltage switch logic that is AND or NAND gate. So this is actually cascode and a NAND gate. Now we can observe that how the pull down networks are complementary with parallel transistor. So the pull down network, if you can see here, are complementary and with parallel transistor in one and series in other. This figure 9.2c that we can see here shows a 4 input XOR gate actually. The pull down network share A and A complement transistor, that means the inverter transistor, to reduce the transistor count by 2. Now, sharing is often possible in complex function, and the systematic methods exist to design the shared networks. Now, this cascode voltage switch logic that we call it abbreviate also called CVSL has a potential speed event because of the logic is performed with the NMOS transistor and that reducing the input capacitance. Now, as in the pseudo NMOS, the size of the NMOS transistor and size of the PMOS transistor is important. Now, it fights the pull down network, so a large PMOS transistor will slow the falling transition. Now, unlike pseudo NMOS, the feedback tends to turn up the PMOS, so the outputs will settle eventually to legal logic level. Now, a small PMOS transistor is slow at pulling the complementary output high. Now, in addition to this cathode voltage switch logic gate requires both the low and high going transition and adding more delay. And conventionally, current during the switching period also increases the power consumption. Okay, so that is the main cases where we can found the logic behind cascade voltage switch. So the pseudo NMOS work well for wide knot structure. Now this cascade voltage switch logic also requires the complement a slow, tall, and NAND structure. Therefore, this cascade voltage switch logic is poorly suited to general NAND and LON logic. Even for symmetric structures like XOR gate, okay, it tends to be slower than the static signals, as well as more, you can say, power hungry. Okay, so however, the ideas behind CBSL helps us to understand the complementary path transistor logic, which we can discuss in later period of time. Okay. So this is actually the idea behind cascode voltage switch logic. Now it is very important. We'll go to one other content of this syllabus that to study about nano device characterization. Okay. Now why it is very important? Why we need characterization actually? Because when we do any characterize means to know something about about something like we sometimes we tell the what is the character of this person, right? Or what is the character of this is plant. Okay, what is the character of this species, right? What do you mean? What you mean by that? We need to specify something, right? We need to know something, so that we call it characterization. Now, in CMOS device circuit, our characterization is basically the characterization that we are fabricate the devices which we generally fabricated, right? So the device which we have fabricated, we need to characterize. Otherwise, how can we get to know that the device is a working device or not, right? So for this one, the nano device characterization is done, and that basically we generally do one important tool that we call in electron microscopy. Now, electron microscopy is a tool where we can able to characterize any nano devices that is fabricated by the normal fabrication technique by let's say for photolithography or electron beam lithography, so that we can characterize. So as already I have discussed that why the electron microscopy is very essential to characterize nano devices, because electron has very high energy, and that high energy helps us to resolve the the devices which we have fabricated, because whatever we devices generally fabricated in CMOS, whether it is PMOS or NMOS or CMOS, whatever the device we generally we fabricate. So that is in the region of either in the micrometer range or nanometer range. Especially it is in the nanometer range, because let's say we talk into consider channel length of let's say 45 nanometer. So you can easily guess that if we don't have that tool to characterize the devices which is of channel length 45 nanometer, then how we can know that yes, the devices is made of 45 nanometer, right? So in that cases we have to characterize the devices, and that is we generally do by electron microscopy. So this is actually the typical this electron microscope. Okay, if you can see here. So I don't know how many of you have seen this instrument, but this is the electron microscope, and specifically this is called transmission electron microscope. This transmission electron microscope here, generally it is operated of the accelerating voltage between 100 kV to 400 kV. Okay, so 400 kV is the maximum accelerating potential, but minimum in the transmission electron microscopy, the minimum accelerating potential is 100 kV. Okay, some instruments it go to 1.1 to 3 MV also, 1 million volt. Okay, but that is a very special case. But normally, the transmission electron microscope, which we generally see, that basically around 100 kb. Generally, it is considered. Okay, 100 kb electron microscope generally considered. Now, this electron microscope has a very high accelerating potential. So, as I have already discussed in the class, using Abbe's equation, that as the accelerating potential will be high, the wavelength will be small. So, as a result of it, the resolution of our the resolution which we will be also improved. So that means if any devices which we have fabricated in the nanometer range, let's say, we can easily characterize using this electron transmission electron microscope. So this one important aspect is that it spread the broad probe across specimen, that it will form image from the transmitted electron. Now diffraction data can be also obtained from the image area. So what about the diffraction data? There is a diffraction of course, and the diffraction data can be obtained from the image area. Now many images types are possible, like this and that uses to select signal sources, and main limitation on resolution, that aberration in the imaging lens. So The here one aspect is that in the TM that the magnification is very high. So that is very important. So for that specifically the electromagnetic lenses are employed inside the electron microscope. So uh, that helps to what you can say the electron beam to focus on the scan areas which we want to see. So that we can do by this electron transmission electron microscope. So this is actually the instruments of electron microscope. So as you can see here, so this is our electron gun. So if you can see, this is the hairpin cathode here. Okay, if you can see my cursor, this is the hairpin cathode. It's very small. This tip diameter is somewhere around uh, nearly 1 to 3 nanometer tip. So you can easily know understand that how the collimated beam can be possible because it is like a hairpin type cathode we generally use. It is an electron emitter, right? The cathode is a electron emitter. So condenser systems like lenses and aperture for controlling the illumination of sample. Now there is a specimen chamber, if you can see here, and that we have objective lens system and image forming lens and projector lens also. Now objective lens system is basically for image forming lens that limit the resolution, aperture, and the aperture controls the image condition, and the projector lens system which we have that actually magnifies the image and diffraction pattern onto the final screen, right? So that actually this electron microscope, especially the transpersonal microscope, is taken into consideration. So if you can see here, can you able to see this image? If you can see this image, this is the image is taken by transmission electron microscope. So this is actually one matrix, that is one composite matrix. It is in the beta phase, nickel, aluminum, and titanium. Okay, so if you can see here, you can see the composite and you can see the grain boundaries here, and we can find the different phases in this here. Okay, you can see this 100 nanometer scale bar. So that means this if you can see this the grain boundary is somewhere around 100 to 150 nanometer. Okay, from the scale bar I can easily estimate. Okay, so this is one example. Another example is that let's say this is one example where the precipitation in an aluminum copper alloy. Okay, but the precipitation is formed in the aluminum copper alloy. We can see here. Let's say we have a dislocation in the super alloy. Okay, and silicon dioxide precipitates particle in silicon. So let's say the silicon dioxide is precipitated in the silicon. We can able to see this images using transmission electron microscope. Okay, so this is one very disadvantages that using the beam of electron beam, high energy electron beam, we can able to see the images very nice way. Now this is actually other example. So laminar chromium nitrogen precipitate is in the stainless steel. So this is one structure, and this is electron diffraction pattern. Okay, so let's say electron diffraction pattern means where the using the electron beam, the diffraction pattern can be obtained on the phosphor skin. Okay, there is a phosphor skin. We can able to see the electron diffraction pattern. So specimen preparation, if you can see, so it can be like the types of the sample can be replicas. It can be like sample like films. It like the film like slices type, or it can be the samples can be powder or the fragment foils. Okay. Now, as if thin enough, ultra microtomy cross and or disperse on the carbon film. So the specimen can be taken in any form. Either it is in the film of powder or it can be fragment foils, slices, films. and then it is to made thin, more thin enough in the ultra microtomy cross. Okay, so that is the instrument called ultra microtomy. We can able to cross it and displace it on the carbon film. Okay, and there is a one carbon foil is there. So 3 millimeter diameter disc, very very thin. So it is around 0.1 to 1 micrometer, even less than. That depends upon the material and voltage. We can able to put our materials over it. We can see. Now these foils actually around 3 millimeter diameter in disc and very very thin. That is I already discussed. So it is around 0.1 to 1 micrometer. Depends on the material and voltage. So mechanical thinning, that we call it grinding, chemical thinning that we call etching, and iron milling that we call it sputtering. So that actually we do in the before specimen preparation. So that means when we want to characterize the samples or specimen using this transmission electron microscope, we need to prepare the samples accordingly. So this is the exam design around perforation. So it's an example where we can want to see the region around perforation. Now this is actually diffraction, that is electron diffraction. So this is using Bragg's law called, which is lambda is equal to 2d sine theta, where lambda is the wavelength of the electron beam, and t the interplanar distance, sine theta, theta is the Bragg's angle, and so within this we can able to find different diffraction data accordingly. So these are all actually some. I want to show you that here some of the diffraction point which you can see here. That how the diffraction, the point actually which you can see here on this screen. Actually, basically the diffraction from the plane. Okay, from each plane, whatever it is diffracted, the electron wave diffracted, we can find the spot on the screen. That actually our diffraction data. So this is not required for you. Okay, so this is all about that. I was just want to show you that how uh, this want to characterize any devices using electron microscope, so that we can able to do. If you can see in the previous slide, in the fabrication here. Okay, so here this is actually the that I already discussed. This is actually the clean room actually. So actually this is actually one electron microscope, that is, but this is called, we call it FESM, field in emission scattering electron microscope. So in this cases, whatever the devices we generally fabricated, so that we can able to characterize. Okay, so the characterization we can do, and because whatever the devices we generally fabricated, we need to know how the devices is made. So for that we need to have such kind of facilities, and for that we need to have the electron beam of sufficient energy. So that I just discussed, that is actually 100 kb electron gun, but here this is actually 30 kb electron gun we generally employ. Okay, So this is actually the in this way we can able to see the samples which you want to characterize. Okay, so this is for today's session. So so we'll meet on Tuesday. Okay, I think there is no class tomorrow, right? There is no class tomorrow. Okay, so then we'll meet on Tuesday at 10:45 a.m. Okay.